So, welcome to our second seminar, which is going to be hybrid this time, and it's Lior Alon, and he will talk about universality of the nodal statistics for metric graphs.
Thank you very much, and thank you for inviting me to give a talk. And also, I want to say that I was a bit excited about giving this talk. It's the first time that I'm giving this talk and my first talk here in the Institute as a member. And I actually couldn't decide on which topic I'm going to discuss after I'm going to present the new results. So I made two options, and I will ask you to choose.
Are you allowed to vote?
What?
Are you allowing mail votes for people in the Zoom or only people here?
People here have are counted twice, but so I'm going to talk about an improvement towards universality of the nodal statistics for metric graphs. That's a joint work with Rami Band and Ergodicity. And first, I'm going to do a very brief introduction about nodal count. So I think that probably one of the first rigorous results about nodal count is that if we consider the solution, the one-dimensional solutions of minus the second derivative equal to lambda f from the interval with these boundary conditions. So Sturm was able, is there a, no.
Try smacking it in your hand. Sometimes I believe it.
Yep,
wow.
that was. So Sturm already in 1836 showed that the number of points where a function vanishes is equal to its spectral position. What I call spectral position, it means on which solution are we talking about when we're ordering them according to their eigenvalues. So this means that when you look at such a wave function, such a solution, and you are nobody tells you this is the end solution, you can actually just count the intersection with zero and see on which solution are we talking about. Now, I'm going to talk about the generalization for metric graphs, but let me first go to the standard generalization to nodal domains in the plane. And we have the Dirichlet problem. We have the Laplacian of f equal to lambda f. And once we get a solution, then we can talk about the nodal domains now, the domains where the function is either negative or positive. And the standard thing is to get this checkerboard pattern, which is very intuitively, physically, and you expect to get as the eigenvalue grows, you expect to get more and more of these squares, but actually it's very unstable, and we can take the same eigenvalue with a different eigenfunction and get a very different number of nodal domains. So this instability makes it a very hard problem, and if we, to make it formal, if we take a complete set of solution, fn's, ordered according to their eigenvalues, phi n is the number of nodal domains, then we had at 1923 the current result saying that phi n is always less or equal than n, which we can write it like that. And the next result was by Lior in 56, saying that, yeah, this might happen, but only a finite number of time. And in the limit, asymptotically, this phi n over n is actually bounded by a lower bound, which was shown by Bourgain and Steinberger to be not a tight bound. But what I want to talk about is not the actual bound, but the entire behavior of this quantity, this phi over n, which is what we call the nodal statistics.
Let me go back to that previous slide. So does this have to do, so that's the Bessel function there?
Yeah, exactly. That's the first
So
zero.
this is what you see in the disk or what?
Yeah, exactly. That's the one. But again, it's not relevant actually to our talk. It's just as a motivation. So in 2002, Bloom, Knutzman, Smilansky noticed something in the numerics that if you're looking at the behavior of this quantity, phi n over m, it's actually distributed according to some universal behavior, actually two different universal behaviors that distinguish between chaotic and integrable domains.
This is the large n limit, right?
Yeah. Now, I call it the nodal BGS conjecture because it's Bloom, Knutzman, and Smilansky, and because it's, for those who know what's the BGS conjecture, it's very similar in a way. And for integrable domain, they were able to prove it. It's the easy part all the time, but actually for...
What do you mean by integrable domain?
Again, I don't want to... I really don't want to get into it. It's just for the...
Background, right?
Just for the motivation. For the chaotic case, the generic case, Bogomolmi and Schmidt at the same time use a random wave argument saying that such an eigenfunction should look like locally like an eigenfunction taken from some kind of random wave ensemble, and they use some kind of a percolation model to predict that for chaotic domains, this phi n should behave like a Gaussian with both mean and variance of order n. Now, on 2009, Nazarov and Sotin were able to prove it. What? On 2009, Nazarov and Sotin were able to prove that such a result only for the mean for random spherical harmonics, not chaotic domains. And lately, just 3 or 4 months ago, they uploaded to the archive a new proof for the variance, but that's like the top of what we can say about this, and it is still wide open.
This is just for random spherical harmonics, right?
Yeah, that's just for random spherical harmonic, not for random waves in general, and not merely for chaotic domains.
Okay.
Now, that's where we're going back to Sturm, and instead of going to the two-dimensional case, we're going to the metric graphs case. So let's talk about metric graphs. What do I mean? Given a finite graph, so we just take a bunch of edges, segments on which we can solve our differential equation, and we glue them together according to some graph structure. And we will have each edge would be of a possibly different edge length. So we talk about L as the number of edge lengths. And for this situation, we can talk about the Laplacian. So it's just minus the second derivative on every edge. At this point, it's not yet self-adjoint. In order for it to become self-adjoint, we need certain vertex conditions. That's the analog of boundary conditions. And it's going to be continuity at each vertex, and some of incoming derivatives on each vertex must vanish. Using this thing, we get a complete family of eigenfunctions, infinite number. Although it's a finite, compact, connected graph, we get infinite number because it is a continuous object. We get our eigenvalues, which we always order and talk about their square root. It will be much more convenient. And now we can talk about the nodal count. And now you can see that the nodal count is no longer phi n equal to n, as we are used to. And you can see here just an example which numerically I ran. You can see here an example where it is phi n equal to n, but here and here, it's actually phi n equal to n plus 1. Now, the heuristic here is that it's not going to be equal to n all the time, but it's not going to be very far from n. So actually, Gnussman, Smilansky, and Weber show that phi n is of order of n with a uniformly bounded deviation, this phi n minus n. So phi n minus n is some kind of a deviation which is what we find interesting. So this is the chaotic part that's going to fluctuate, and we want to look at it. And they conjectured already there in the 2003 that for metric graphs with rationally independent edge length, the distribution of phi n over n of this deviation approaches a Gaussian distribution for large, well-connected graphs. This was very, very ill-defined, this conjecture, and actually the only reason that I know about this conjecture is that we conjectured it about a year or two ago, and during my thesis, I worked a lot about I dug a lot of things from the past, and I found it by mistake, and then I talked both with Gnussman and Smilansky, and both completely forgot that they conjectured it. But just for you to see, so in 2003, and I'm going to talk about it soon.
This is a deterministic statement, right?
Yeah.
Essentially a deterministic statement.
Yeah. So in 2003, they didn't have any numerical evidence for that. And I will explain why it's very hard to give numerical evidence for such a thing. Here is my numerical evidence, and I hope you can see. So here are the distributions of this value. When I take, I sample something like I sample a million eigenfunctions for each one of the complete graphs from 4 to 15 vertices, given some kind of rational independent edge length. And you can see how when the graph grows, this thing becomes more and more Gaussian-like. Now,
could you clarify? Could you clarify what the growing graphs in your numerics are?
Here, what you're looking at are complete graphs with 4 to 15 vertices. So that's you take a number of vertices.
So complete graphs. I mean, the original statement seems to be independent of anything. You're making complete graphs. Yeah.
Yeah, I will get into I will get much deeper into the numerics in a few slides. This is just a heuristic. So from now on, I'm going to assume that all graphs has no loops. All the grids are going to be, I will only have degree 2 vertices, and I'm not looking at the graph which is just a single loop. So let's assume we have more than one edge. This is only to make all the statements nice without all kinds of, but everything goes for all graphs, but I don't want to get into technical details.
No assumptions on the length of the edges.
I will get to that. Okay, so definitions. An eigenfunction would be called generic if the eigenvalue is simple and the eigenfunction doesn't vanish on vertices. In this way, I can talk about this nodal surplus, which is phi n minus n. I want it to be simple so that n will be well defined. I want it not vanishing on vertices so that the nodal count would be well defined. And it's actually something that we need. Can you see that? Is the way to get this out of the way? Mm. So what you can see here that we prove that this is actually generic. So if you take the edges to be rationally independent, the indices for which Fn is generic has density 1. So it's logical to talk about it. Now, Gnussman, Smilansky, and Weber gave an upper bound on this deviation. The Kolaiko gave a lower bound on this deviation. And we can now say that this deviation is always between 0 and beta, where beta is the first Betti number of the graph. the first petty number of the graph is going to play an important role throughout this talk. And now that we have all those things, we can actually talk about what is the nodal distribution. So we are going to look at the deviations and try to capture what the frequency of appearance of a certain deviation. So we're going to say that the probability to get sigma equal to j is just taking the number of times we get sigma equal to j out of the first n eigenfunction, divide by n, and take n to infinity. Now this limit not necessarily need to exist, and we have a statement that says if there's a rationally independent, then these limits exist. We have a well-defined nodal distribution, and moreover, we even have a symmetry. So we always have that P of sigma equal to j is equal to P of sigma equal to beta minus j. Now that's
again, sigma is the number of nodal minus n.
Yeah.
It's nominal.
Yeah. So where am I? Okay. So now we can state the conjecture in a more rigorous way. So our conjecture is as follows. So under the assumption of rationally independent edge lengths, and that's the only assumption that we have. So it's, I guess that Peter will now say that it's probably not true because there must be some sequence of bad graphs, but at the moment we believe there is no. So under this assumption, the nodal distribution is going to approach to a Gaussian distribution where we can actually say that the mean is going to be beta over 2 because of the symmetry.
Thank you very much.
What? So the mean is going to be beta over 2 because of the symmetry, and the variance is going to be of order beta. It's going to grow linearly with beta, and the limit that we are talking about now is the limit of beta goes to infinity. Okay, so we're taking larger and larger graphs, but larger in the sense that we get more and more cycles in the graph. It's not just taking a tree to infinity. And this is the convergence that we're talking about in distribution, of course. And
you're just taking any sequence.
Yeah, that's the conjecture. Now, let me talk about what we have so far.
Mm-hmm.
So first, a previous result from 2017, if the graphs that we're looking at are trees of cycles, meaning that whenever I have I have two cycles, they are disjoint. They're not connected by any. They don't share any vertex. Then it's like a tree structure with cycles. In such a case, I can say exactly that the nodal distribution is going to be binomial, which means it's going to converge to Gaussian as I want.
But so from your picture, it's not clear. Okay, so there's okay, but your definition, it cannot be closed by something else because then it would be something bigger which shares. Okay, yeah.
Yeah. No, that's actually.
So they have to be all isolated.
Yeah.
And not reconnect.
Yeah.
Okay.
So the way that we define it, I can always have an edge. I can always remove an edge. I can always as a cut which separates between two cycles. And that's what the proof uses. And this is the only case where we can actually calculate this distribution. Now, our new results, our new numerical result, we have numerical and analytical. The numerical results now, we examine 5 different families. Okay, so the first family that I already showed is complete graphs. The second family is periodic ladder graph. I will draw it in a minute. Then we're talking about periodic square lattices, random regular graphs, and random Erdős-Renyi graph. What I was aiming in this numerics was to cover as much ground as I can. And for every graph, we chose random edge length of incommensurate, of rationally independent, and sampled, and I'm going to talk about this sampled thing, 10 to the 6 eigenfunctions. Now let us look at the pictures. So here are the complete graphs, and you can see this nice behavior. Here are the ladder graphs, so that's just taking such a ladder and identifying these two edges with these two edges. And I'm taking the number of steps to be 5, 10, 14, 15, 18, and 22. Notice that this is a 3 regular graph.
And the lengths of the edges, you're making those, how are you choosing those, right?
I just choose randomly,
Randomly.
and I choose them. I make sure that they are edge length independent, that they are length independent.
Yeah.
As part of the proof that we actually do, we can show that in this case and in some of the other cases that I'm going to see, once I have enough symmetry for the discrete underlying graph, then I can show that it's going to be independent of the choice of edge length.
Just curious, actually, you make them
Independent of the choice of edge
the
length.
rationale.
Yeah, but that's you need certain symmetries of the discrete graph underlying.
Remember that you said something that they should be independent over the rational.
Yeah,
Now, how do you do computation of numbers which are independent over the rationals if you can work only with rational numbers?
that's a good question, and that's also one of the things that I'm going to talk about, and that's why the numerics that I'm doing here is much better than any previous thing that we did before. Periodic square lattices, where we have like Z2 mod 4 up to 4, 5, 6, and 7. And well, so far everything is boring because you can see everything looks the same. Everything has the same behavior. And here are 5 regular graphs. So by the way, this was 3 regular, this is 4 regular, this is 5 regular.
So this is all numerics or
Everything numerics.
Okay.
And
can you do something with a ladder explicitly or not?
no. And these are Erdos-Reini graphs. I don't know why it's wrote Erdos like that. It's supposed to be the weird thingy.
Yeah.
And here by Erdos-Reini, I mean that I take the number of vertices to be either 9, 10, 11, or 12, and each 2 vertices are connected by an edge with probability 0.75. I took the probability to be high because I want to make sure that the graph is connected. And now just to have something quantitative, so here are the measure of the Kolmogorov-Smirnov distance. That's the only way I know how to compare a discrete probability distribution with a continuous one. And you can see how it goes down, where here you can see the Betty number, and as the Betty number goes up, you can see it goes down no matter on which sample are we looking at. And here, this is what really was very, very surprising for us. The variance were really linear in beta. And we actually saw a very nice correlation between the degree of the vertices. So this is an ongoing work about trying to understand what's the coefficient of the slope and why is it related to the degrees. And okay, so far that's the numerical evidence that I want to show you, and that's the first time we are able to produce such a mass numerical evidence. And now I want to talk about the analytical evidence. So recall that we had this thing, and it was very important to separate between the cycles. So now we wanted to do something which is getting the cycle as close together as possible. And so these are the families of graphs for which we were able to show that we get such a convergence to Gaussian. Now, just to explain what's the thing here, for these 2 families of graphs, these are the only cases where we can actually give an explicit calculation saying that if you have this eigenvalue, if this eigenvalue is equal to k, then its nodal surplus is going to equal to something. These are the only two options where we can actually do that. We cannot say exactly what is the distribution, but we can evaluate it. For this one, we just did some kind of rank 1 perturbation method to show that we can get from this proof to this proof, but getting from there onward seems impossible. And for this situation, we can show that these distributions are not binomial, but they do converge nicely to what we want. And now that's the point where I wanted to ask you if you want me to. How much time do I have?
Half an hour, more than half an hour.
Great. So whether I should pick one of those examples, say the watermelon, and do a concrete example of how such a calculation can be done, what we use, and talk about the edge length dependence, or talk about the sampling method and actually the ergodicity and the machinery and the secular manifold, the whole machinery behind what's happening here and why it was so hard to do it numerically up to this point. So if anyone has a certain preference.
Second.
Okay.
Yeah, I have that preference too.
Okay, so let's talk about a theorem behind the sampling and why can we even do it? We cannot have actually a rationally independent thing in a computer. And how can we estimate over 1 million eigenfunctions? So in order to do that, let me first introduce some definitions. So given a graph gamma, this is a discrete graph, no metric yet. We get a family of 2e dimensional unitary evolutions. E is the number of edges. Unitary evolution matrices, that's how we call them. U kappa alpha, where kappa is a coordinate on the e-dimensional torus. Alpha is a coordinate on the, that's a mistake, that's a beta, first Bethe number coordinate torus. And this evolution matrix depends linearly on the exponents e to the I k e, kappa e, and e to the I alpha j. I won't get into the technical detail of how do we get this and what's the meaning of this for whoever wants. That's a very interesting thing. But for the moment, I'm just defining it like this. And once we have that, we can talk about the kappa alpha dependent eigenvalues. So e to the I delta n goes from 1 to 2e are the eigenvalues of this matrix. And it's unitary, and these are the eigenvectors. I'm going to denote the Hessian of theta n with respect to alpha at alpha equal to 0 as this. And this is how I'm going to denote the Morse index, namely the number of negative eigenvalues.
No, I still need to understand something about this,
Yeah.
this unitary, because otherwise I won't have any orientation. So these unitaries are generated from the Hamiltonian with various boundary conditions?
No.
Okay.
This problem, the way that we solve this problem is actually we start from solving eigenfunctions. Let me do it here, although people on the Zoom won't see it. So if you're looking at a solution of an eigenfunction at a single edge, you would get something of this form, A times, let's say it's going to be A times e to the ikx plus b e to the minus ikx. And then you get a vector of coefficients. And that's, as always, we want to get something algebraic.
So it's made from that.
And then we get some kind of scattering matrix. So we get this, we get a solution that looks like e to the I sum of kappa e, let's call it IE, e to the I sum over alpha j zj. So these are generators, these are matrices. This is a unitary matrix. These are the generators, which I'm taking into exponent, times some kind of a fixed matrix. This is where the topology of the graphs kicks in. It's kind of like an adjacency matrix, but not exactly. And I get this equation. So, and this whole thing, I call it the unitary evolution matrix. So it's going to be a family of matrices, depends on those kappas and alphas. And its eigenvalue 1 solutions are going to be the coefficients of some eigenfunction. So this is how I'm going to go around all possible eigenfunctions. Now this is going to be a notation of a Morse index. And what the theorem that I want to try to show you is saying is the following. So given a graph with rational independent edge length, and consider this matrix, which is just diagonal with the edge length on the diagonal. Then the nodal distribution is given as follows. So again, this is the limit that we talked about of the number of times I see sigma n equal to j, the average number of time when I take big N to infinity. That's going to be an integral over the e-dimensional torus, with dk here is a normalized, the normalized Lebesgue measure. For every k, I'm going to look at all of the eigenvalues of the unitary evolution matrix at that point. I'm going to look at each one of them. I'm going to compute the Hessian with respect to the alphas at alpha equal to 0. And I'm going to look at the Morse index of that. And I'm counting how many of these guys going to have Morse index equal to j. Each one with
Just
a weight
Can you
given by
clarify?
that.
I have a
Yeah.
question.
Yeah.
Kappa is the lengths, right?
Yeah, kappa is the analog of the...
And
of
the alphas are just deformed near the origin, nowhere else. Is that correct?
Yeah, the alpha is
The
what...
second bunch of variables is just a deformation at the origin that's important.
Yeah, and the alpha is what's related to one forms, to deformations of the Laplacian using one forms, what we call magnetic perturbations.
Right, but you had introduced twice, I guess E was beta, E is beta, right? Capital E.
No. That's, here I'm counting over the eigenvalues of the unitary evolution matrix. So the unitary evolution matrix is a 2E by 2E matrix. It has 2E eigenvalues.
Sorry, what I'm saying is you introduced two tori.
Oh, yeah.
So what I'm saying, I just want to make clear that the one torus that you introduced, which I'm not familiar with the alphas, is only studied at the origin.
Yeah, this one, and it's a beta. It's not E, it's beta. That was a mistake. And we're only looking at it around the origin.
Okay.
We're only looking at the neighborhood around the origin. Thank you.
Well, for the kappa, the whole torus is very relevant all the time. Yeah.
Yeah, we're integrating, we're averaging over the entire torus here.
Okay.
Okay, now, okay, so here, what I actually do in the numerics is study this thing, where in this thing, whether my edge lengths are rationally independent or not is really not that important. It's actually continuous in the edge length, so nothing bad happens if I have some kind of a numerical mistake. And what we actually do is just taking this thing, which I just explained what's in here, and sampling it uniformly with random kappas from the torus. So this has several advantages. So first thing, and most importantly, I would say, it's not sensitive to numerical errors. It doesn't care if my edge lengths are actually rationally independent or not. They're
But
rationally
you're
independent.
using randomness here though, right? Or not? You have a random K.
Here no, here yes. When I sample it,
Yeah.
it's much better to sample it than to actually calculate, trying to estimate the integral.
Oh, I see. That's just to do the integral.
Yeah,
Then okay. So, but that's the formula up there with that's deterministic, and then
this is totally
Okay.
deterministic. Again, I'm using ergodicity here to go from.
Yeah.
I would talk about it. The second thing is the convergence rate is much better. I don't need this having the first million eigenfunctions and then to ask myself whether I'm at the limiting distribution or not and whether I need to take more. And it converges much faster. And the last thing which I'm going to talk about is actually that this Hessian, I can estimate it using second order perturbations, using only this data which is local. Why local is good? Because here phi n minus n is not something which is local. N is actually something which is very, very hard to determine and is very, very sensitive is very, very numerically sensitive. If I lost an eigenvalue in my count, if there was a multiplicity that I missed, then everything changes. Okay, so how do we, before getting into proving this theorem, which is the main thing here, let me just explain how we get the Hessian, which is something that I also wanted to show because I think that it gives us some kind of a nice glimpse and thing that happened here in the background. So denote the alpha generators by ZJs. So these are generators in the sense that when I take the derivative with respect to alpha j, I get this I times this matrix outside. And this is some kind of a generalized Cayley transform. So this is just something that transforms the eigenvalues from the unit circle to the line. And I'm going to act on the unitary matrices. So here I cannot really inverse because this might be not invertible. So I'm using the Moore-Penrose inverse. Here's a new Nobel Prize winner. And for almost every kappa, that's almost every kappa because I want the theta n to be of a simple eigenvalue. So for almost every kappa, this Hessian is going to be equal to this nice thing. And that's something which I really like because here you can see some kind of a tensor inside the trace, tensor which couples a bilinear form that acts on the homology. The Zi and Zj, here the Hessian is a bilinear form that acts on the one forms, on the homology. And Pn, or this thing, is a bilinear, we're looking at the bilinear form that acts on the 2E space on the space of the coefficients of the eigenfunctions. So this is very related to the works that we can see in the nodal magnetic relations, where somehow the properties of the eigenfunctions and the properties of the eigenvalue with respect to changes of magnetic perturbations are related through these kind of objects. Okay, so that's just about that, and this is a standard calculation. Now let me talk about the proof of this. How do we show this kind of thing? And to do it, we're based on the proof is based on three ingredients. So the first one is ergodicity on the secular manifold. Second one is nodal magnetic relation. So ergodicity is what enables me to go from discounting over here to some integration over the secular manifold. But I don't want to integrate over the secular manifold, I want to integrate over the torus. The nodal magnetic relation is what enables me, instead of talking about a nodal surplus, to talk about a certain magnetic index. And eventually, in order to go to integration over the torus, I'm going to talk about some kind of periodic orbits of these unitary matrices, where I just give them some kind of a phase. So let's start with a secular equation. So that's what we talked about earlier, where I showed you there. So when we start and we want to solve such an equation, such f double prime, the second derivative is minus k square f, then we can do a trivial ansatz and says that on every edge, f looks like that, which means that we have some kind of a vector of coefficients that describe the eigenfunction, and the vertex conditions. So the eigenfunction has to satisfy both this and vertex conditions. So the vertex conditions are going to be a linear equation on this coefficient. What linear equation? Exactly this one, meaning that the coefficients of an eigenfunction, the coefficients are coefficients of an eigenfunction if and only if it's an eigenvalue of it's an eigenvector of eigenvalue 1 of some unitary evolution matrix. And this actually gives me an isomorphism between two eigenspaces. I have the eigenspace of eigenfunction with eigenvalue k squared over the metric graph, and the eigenspace, this is the eigenspace of eigenvectors of eigenvalue 1 of this unitary evolution matrix. Using this, I'm going back to the slide I showed at the show talk. We get the following equation, which we call the secular equation. K squared is an eigenvalue if and only if the determinant of 1 minus u kl is equal to 0. This is the trigonometric polynomial that you might heard Peter talks about. And again, the whole properties of the graph gets into the u here. Now the secular manifold is going to be the zero set of this function as a function of kappa. At this point, the alphas are all 0. And if I say that this is the zero set of this determinant, and here I'm looking at the point k times L, so I get the picture that k squared is an eigenvalue if and only if this flow of k times L modulo 2 pi, where k is the thing that changed, lies in sigma, which is this nice picture. So consider this graph. This would be its manifold. The black line would be the line of k, varying k in the direction of L. And whenever we hit the manifold, we get an intersection, we would get an eigenvalue. This would be k1 of L. The next one would be k2 of L, k2 times L, k3, k4, etc. Now, why is this handy? Because now we can talk about ergodicity. So this sequence of hitting points, these hitting points are going to, once the edge lengths are rationally independent, these hitting points are going to be equidistributed on this manifold according to some measure, which we call the Barra-Gaspar measure. And this what's enabled us to do, to go from counting eigenvalues and eigenfunctions to do some kind of an integration against this measure on the secular manifold. Using this, we were able to say,
you haven't taken any large n limit. This is an actual count, right?
But no, but here you're talking about, you have equidistribution, right? So equidistribution means that in the limit, if you have, we're looking at this and say that I take a color here, some kind of a set.
Yeah.
And I want to say, okay, the limiting time that I hit
is the measure of that set, right?
Is the measure of this set, but it's a limit of n goes to infinity.
Oh,
I think, Tom,
yeah.
I think Tom means that you haven't taken the limit of the torus. The graph's fixed.
No. That's the graph is fixed. The graph is fixed, the number of edges.
Yeah.
But I do take a spectral limit.
Yeah.
So that's a
Otherwise
analysis.
you can't apply the ergodicity, right?
Yeah.
Okay.
Okay, so now once we have this, we have the theorem. This theorem is based on we actually needed here the nodal magnetic relation, saying the following. So the nodal surplus can be realized as a function on an open dense set of sigma. Now, what do I mean by that? I mean that I can color here a set where I say, okay, whenever I hit this region, the nodal surplus is going to be 2. No matter what are the edge lengths, in which direction I'm going, and how much time I traveled along this line. If I hit this region, the nodal surplus is going to be 2, and then I can measure this. So we get such a function, and we can measure its level sets. And the measure of its level set, the Barra-Gaspar measure of those level sets, is exactly the nodal distribution. So this what actually proved that the nodal distribution exists. And using some kind of inversion argument, we were able to produce the symmetry in here.
What is this measure? Is this a complicated measure?
No. This measure is actually the simplest thing that you would expect. So this measure is going to be just the cross section, a normalized cross section area. So if you're going in this direction, so you take a set, you project it orthogonal to this direction, and you say what's the area, and you normalize it. But it's very related to the direction in which you go. This measure. I'm going to talk about it. So again, by the nodal magnetic theorem. Okay, so by that point, I was going to state the nodal magnetic theorem on the board, but I guess that people on the Zoom cannot see. So I will state it. I hope you can read it, but the nodal magnetic theorem says the following. It says if Fn is generic and if Fn is generic, then Kn, the eigenvalue, is a critical point of the extension Kn as a function of alpha around alpha at alpha equal to 0. So that's exactly, I take an eigenvalue, now I perturb my operator, I insert some kind of parameters, there's alpha, and the eigenvalue is going to be a critical point of this manifold at alpha equal to 0. And if it's a critical point, we can talk about its Morse index. The Morse index, the Morse index of Kn of Kn, which means that the number of negative eigenvalues of its Hessian is going to be equal to the nodal surplus. So this is the nodal magnetic connection, meaning that this property, this nodal surplus that we're looking at, is actually a stability index of the eigenvalues with respect to magnetic perturbations. Now, since we have this implicit function,
Question. So just to be clear, for any given graph, there's a unique, and for the generic angle L, there's a unique distribution, which, and then the second question is, when you let the graphs get larger or the Betty numbers get larger, does this distribution become Gaussian? So there are two, you already have the existence for any given one.
Yeah, the existence with a symmetry, which means that I know where it's mean, but now I want to say something about the limiting.
Right.
So once we have this implicit function, we can, instead of talking about the Hessian, the Morse index of K with respect to alpha, we can talk about the Morse index of theta of the eigenvalues of the unitary evolution matrix. So again, we want to go from the picture, we want to go from the analysis picture to the algebraic picture. So I want to take the derivatives with respect to the eigenvalues of the unitary evolution matrix. So this gives me this function which I talked about, the realization of a function on the secular manifold. Now that I have this, I can talk about the last piece. So the last piece is going to be this one, the orbit of just acting with S1 on the torus, taking e to the minus I theta times the unitary evolution matrix. So when I say orbit of kappa, I mean take kappa plus theta modulo 2 pi. That's in each one of the coordinates. And I have some kind of a technical lemma that says that this Barra-Gaspar measure, using which I'm doing the spectral averages, I can calculate it, instead of calculating over the manifold with this measure, which is a very hard thing to do explicitly, I can just average the entire torus, where whenever I get a kappa, I go along the orbit. I see all the intersection points of this orbit. So here I'm integrating over the starting point of the orbit. For each starting point of the orbit, I'm going to intersect this set. And for each intersection, I'm going to give this weight. And this is going to be the new measure. Now, why is it nice? Because it's very easy to see that these intersection points are exactly going to be kappa minus those theta n's. Because I'm asking, when does this thing has an eigenvalue 1? So if I take just this and I just plug in theta n, I would get an eigenvalue 1 at the point kappa minus theta n. So this gives me a way of measuring this. And now plugging all of these things together, all of the three ingredients, I get my nice formula. So again, the ergodicity gave me a way of saying that this is actually the integration over the manifold of mu L. Now I want to talk about this. I want to say two things. What is the measure? How do I measure? And what is this set? So how do I measure? I take the orbit. And what is this set? I'm looking at the Hessian. And this is how I get this nice formula using which we were able to get an actual sampling and actually do the numerics, which people haven't been able to do so far. And we can actually just to have a sense of what does it mean. Up to this point, we were able to sample graphs with something like 4, 5, 6 edges at most. Now I'm able to go to graphs with almost 100 edges. And so the prediction is much better, but
and the sampling converges rapidly?
Yeah, this sampling converges very rapidly. So I'm always taking something around 1 million samples, but it's you usually need much less. You need less.
Now, I'm sorry, I got lost all this notation, but what is the L again? The
L?
Yeah, the capital L.
So here is where the edge length gets into the point. So that's the weights. L is a metric with the edge length on the diagonal.
Oh, that's all. Okay.
That's all. So it's only the weights.
Okay.
The weights that are changes according to the edge length. How much time do I have?
5 minutes.
5 minutes? Okay, so I pretty much wanted to end at this point, but if I have another 5 minutes, I just want to say another thing about that's something that I wanted to show if I would show the...
Let's go back to that formula if we could.
Yeah.
So this formula is just very generally valid as long as you have these irrational no rational relations among the lengths, right?
So first of all, this is equal to that for any choice of edge length.
Okay.
But to say that it's equal to the nodal distribution, you need the rational independent edge length.
So you can apply the ergodicity.
So you can apply the ergodicity, yeah.
Okay. So now the problem of so your problem is really, you can test this numerically, but if you want to prove something, you got to find some other way of actually checking that it's normal as you predict, right?
Yeah.
So you have to have some other technique for that.
Totally other technique. Although and that's what I wanted to show in the other. But for example, one of the things that I was talking about in my short talk about we have some kind of conjecture that at some limit we expect to see the level spacing distribution behaves like a Gaussian ensemble. So to show something like that would be exactly going to the same thing, only now, instead of looking at the Morse index of the Hessian, what you would want to sample here would be the difference between theta n to theta n minus 1.
Yeah.
Right? Because we would like to measure these distances. Mm-hmm. This would be the level spacing.
You mean if you want, local distribution.
So actually this gives us a very, very useful tool to convert everything that we're talking about to investigation of this cluster of unitary matrices, which we can look at as some kind of a random matrix ensemble, in a sense. And that's why, so for example, another thought, if we want to talk about questions like quantum unique ergodicity. Quantum unique ergodicity would be like asking the analog of quantum unique ergodicity would be that those eigenvalues, those eigenvectors are going to be of the absolute value of the coordinates of those eigenvectors are going to be all of the same size, which if these are eigenvectors of a random unitary matrix, we would expect something like that when the matrix grows large, right? So that's another. So there are a lot of things that we can use random matrix theory applied to this unitary ensemble in order to get things about the functions, and everything goes through this machinery.
Okay.
And maybe the last thing that I would want to show is that we have a nice theorem here that we actually use. And here I'm just showing a simple case, but we have a much better, much larger case where you can talk about the symmetry group. Here I'm talking about the symmetry group of the discrete graph, not the metric graph. The symmetry group of this discrete graph acts on the secular manifold, acts on the torus. And if the symmetry group acts transitively on the edges, so for example, in the complete graph, in the ladder graphs, we had something which is almost transitive. So in such cases, this is going to be L independent. And it's a very nice argument because essentially one of the things that you can see in this picture that I showed you is that the L dependence here is convex, is a convex sum of normalized measures. So I can take out the L dependence here outside and show that whenever I measure here something, I'm looking at the convex sum of measures. And I can exploit this to give a lot of stuff. So I think I'll end at this point.